This is the 5-4 notes for Precalculus 2. This section basically deals with another set of unique formulas, specifically called product to sum formulas and sum to product formulas. So both ways. We'll cover both of those throughout the course of the lesson. But essentially, let's say you were given over here the product of two trig functions and you were asked to change it into a sum or difference, then what would that look like? Well, you can see in the picture in the formulas that that's basically what you would do. Again, this is all about application and being able to manipulate trig function formulas. So before we do anything though, I think it would be valuable to be able to just prove that one of, like for instance this one. So this first formula, I think it would be valuable to prove that this is actually true. So what's interesting about this is if you look here and here, we actually have formulas for the cosine of a difference and the cosine of a sum. So that's from our section 5.2, I believe, our section we just went through, where we can actually use those formulas. So what I'm going to do is I'm going to create a proof here where we're going to start on the right hand side of this formula and we're going to prove that it's equal to sine alpha sine beta. So before we do anything with that though, we want to return to our previous sections where we talked about what the cosine of a difference and the cosine of a sum will be. Well, the cosine of a difference, if you recall, starts with the double cosine of the respective angles, and it always has the opposite SIGN sign, and then we have the double SINE signs with their unique angles, and the only difference between the difference and the sum is the middle sign SIGN, which is going to be now minus. Okay, so we already know this is true from previous sections, so let's use that to prove this formula. So all I'm going to do is I'm going to take since cosine of alpha minus beta is right here, I'm going to take what's on the right side and I am going to put it there, right? Same thing with the bottom formula. Since I have cosine of alpha plus beta is equal to this, I'm going to take this and put it there. So let's go ahead and do so. So we're going to get 1/2, little bracket here, and then I'm going to do a parenthesis for the whole setup. So we're going to do cosine alpha, cosine beta, plus sine alpha sine beta, and then we're going to subtract this guy, which is being replaced by the orange expression, and we get this gigantic expression. Now, small thing here, remember we now have this little subtraction sign right here, so just note the subtraction sign has to go to both quantities, right? Here we go with that crazy color again that I picked. So it has to go to both colors, so we're going to, or both expressions because of the distributive property. So let's keep the half. We're going to get cosine alpha, cosine beta, plus sine alpha, sine beta. We'll just copy that down, but now we're going to get cosine alpha, cosine beta, plus sine alpha sine beta with the distributive property. So if you look at this really closely, we actually have, if you look at this, 1, 2, 3, 4 quantities. And if you look really closely, you can see right now, hopefully, that 2 of these quantities actually cancel out. So if you look at this one and this one right here, they actually cancel out one another. So if you keep on going, we're going to get 1/2, and then we have Sine alpha sine beta plus sine alpha sine beta is 2 sine alpha sine beta. And finally, half of 2 is of course 1. So we get sine alpha sine beta. So look at this guy. So we have just proved that the formula here will work on both sides of the equation. So somewhere along the line, obviously somebody, derived these, coming up with these formulas. They're all just ways to manipulate trig functions and go about figuring out different trig methods for doing so. Okay, so how can we apply these formulas? So if you look at, let's say we're given sine x cosine 2x. Okay, so the directions are, let's try expressing the following products as a sum or difference. Okay, so if you look over in the picture, or not in the picture, but in the formulas that are going on up here, if we look for sine cosine, we end up at the third formula. So we need to take that in order to change sine 5x cosine 2x into what's on the right side. So we're basically, I'm going to write it out at the bottom here real quick, so why we have this picture in. So this is going to be equal to 1/2, remember this is alpha and this is beta, 1/2 the sine of our alpha, which is 5x, plus our beta, which is 2x, all plus the sine of our alpha minus beta. Okay, so all we're doing basically is taking this formula and just putting our alphas and betas where they belong. So if we have this, we clearly can collect like terms. So we're going to get half sine of 7x and then sine of 3x as our expression. I'm fine with you leaving this as the answer. Note that this is not equal to sine of 10x. That is not a legal maneuver. So this is okay. Some students might distribute the half to both. That's perfectly fine. I believe in the textbook they provide the answers the way I'm showing it, so I'm just sort of sending you that, or leaving you with that. Okay, so let's try another one. Every once in a while you're going to have a multiple in the front. No big deal. We just sort of keep it along the way. So 4. Okay, we'll keep the 4. And then we go up and we go, well, we have to go to the double cosine one, which is right here, right? So the double cosine one will result in, again, it will be 2 cosines with a difference and a sum. So we're going to write it out just like that down here. So we have a half and another bracket. We have cosine of, remember this is alpha and beta. So we're going to do cosine of alpha minus beta plus cosine of alpha plus beta. Okay, I know there's a lot of brackets. That's not a big deal. Don't get too confused by that. So obviously what's different about this one is this going on here is going to be a half of 4, which is 2. And then we just have to collect like terms here and get cosine of 6x plus cosine of 8x. And again, this is not equal to the cosine of 14x. And we could distribute the 2, but that's okay. So it would be 2 cosine x plus 2 cosine 8x, but we don't need to do that, but this will be okay with the answer. So just to be clear, in both of these problems, we took a product and we changed it into a sum. Okay, so what if we took a similar scenario to this, to the problems we did above here, but this time, instead of variables where the angles go, they're actually radian angles. So what if we were asked to first change this into a sum or difference, then evaluate? Just to be clear, though, we are looking for an exact answer to this, so absolutely no decimals when we're doing these problems. So just as a side note, right now we could find the value of this without using these formulas. So we know what the cosine of pi over 6 is. We can find the sine of 4 pi over 3. You could do that right away. I'm just using this as an example because it's a good example of using the scenario. We'll see an example in number 4 down here where we don't know the sine of pi over 12 or the sine of pi over 12, and we would indeed have to use the formula no matter what. But let's start with one we could find the answer for, with the one in number 3. So again, what we would do is we would go back to the cosine sine value. So if you look at our formulas up here, the cosine sine value is actually here. So we would use this formula with double signs, a minus in the middle, and so forth, and we would do the math out. Remember, we do have a multiple in the beginning here. So we would have a 6 to start, and then we would have the half in our formula. So it's going to be the sine of, remember this is alpha and this is beta, so we're doing the sine of alpha plus beta minus the sine of alpha minus beta. Alright, so if you look at that closely, you can see that we basically have a nice setup. Actually, I'll put a bracket here too. There we go. We have a setup of what we need to do. So just like in the other problem, we can do a little simplifying. First, half of 6 is 3. We also can do this simplification right here by using like terms. So just to be clear, actually, let me do this real quick. Let me save some space for us. So we'll go down here, save some space. So pi over 6 and 4 pi over 3 is the same as pi over 6 plus 8 pi over 6, which is 9 pi over 6. And if we reduce, we get 3 pi over 2. So that means we can change this to the sine of 3 pi over 2. Okay, next, this is going to be, this time, pi over 6 minus 8 pi over 6, which is going to give us negative 7 pi over 6, which this time does not reduce. That's okay. We'll just put it into our expression, as so. So if we look at this problem, we actually have two trig values that are very easily evaluated. So first things first, remember 3 pi over 2 is located at the bottom here at 0, negative 1. So the sine is going to be, in this scenario, the y coordinate, which is negative 1. So we got 3 so far, we got negative 1 right here for this whole expression. Now we need the sine of negative 7 pi over 6. So again, where does negative 7 pi over 6 go? Well, we can go here to negative 6 pi over 6. We go a little bit more to negative 7 pi over 6. So we know we are in the second quadrant where sine is positive. So luckily, for our scenario, we know our result will be positive. But remember, negative 7 pi over 6 has a pi over 6 reference angle at the coordinate, root 3 over 2, 1/2. Remember, sine, we're looking for the y coordinate, which is indeed 1/2. Okay, that should be fluent for you at this point. It makes life a lot easier to be that in terms of what you're doing. If you just do a quick math here with your calculator or a little bit mental math, we're going to do negative 2 over 2 minus 1 over 2 is negative 3 over 2. And if we do the last bit of math here, we're going to get negative 9/2 as our result, which is our exact answer to the problem, staying away from decimals for what we're going to do. Okay, as I promised, what about number 4? So number 4 is more like what I would give on a lab or maybe an exam, because you can't find the result of this, the exact result, to be clear. You cannot find the exact result of this because we don't have special ratios for, or coordinates for pi over 12 and 5 pi over 12. We do have them for the pi over 6 and pi over 3 families. So what does that mean? This method that we're going to do is the only way to find the exact answer to this. Well, there could be other ways, but this is the easiest way to do it at least. So again, what are we doing? We're going back to our formulas. We're going back to our original sine, and we're going to just fill in our alpha and betas as we go. So what does that look like? So remember, this is alpha and this is beta. So it's going to be 1/2 of we're going to have cosine of alpha minus beta minus the cosine of alpha plus beta. All right, so again, we want to do a little bit of like term action here. This is going to give us negative 4 pi over 12, which very nicely reduces to negative pi over 3. This is going to give us 6 pi over 12, which is going to be even nicely more reduced to pi over 2. So if we reduce this, or simplify, we're going to get the cosine of negative pi over 3 minus the cosine of pi over 2. Alright, so again, a little bit of analysis. So our first scenario is we're going to go back negative pi over 3 into quadrant 4. Okay, again, we kind of lucked out here. So cosine is positive here, so we are going to get a positive result. But remember, pi over 3 has the coordinate 1/2 root 3 over 2, and cosine, you're searching for the x coordinate. So we know that'll be we'll know it'll be positive because it's in cosine. So we're going to get first a half, and then a half for the first quantity, minus, well, what about pi over 2? Well, pi over 2 is located at the top at 0, 1, and we want the x coordinate, which is 0. So this is going to end up being a half of a half, which is going to be a fourth. On the other side of the coin, we have the sum to product formulas. So these also can be derived, but it's a little bit longer of a process, so I decided to sort of omit that for the sake of the lesson. The key is, once again, there are 4 of them that represents the sine, the sum and difference of the sines, and the sum and difference of the cosines. Take note that this is not the same as the sine of alpha plus beta. So that is where students will get very hung up on these formulas, is they'll start just doing their basic algebra techniques, which doesn't apply in many cases to the trig expression. So realize that is not the same thing in any way to these scenarios. So if you are given, for example, a scenario where you have the sine of 2 trig functions, you can change that by doing this crazy business over on the right side, and it is crazy business. Take note that only one of them actually ends up being a negative 2 in the front, so just keep track of that when you're using the formulas. So what we're going to do, just like we did last time, is we're going to start out with sort of the easy stuff. So if we, let's say, we wanted a number 5 to find the sine of 7x minus 3x. So we would search for the sine difference formulas going on here. So we would then just say, okay, well, this is clearly alpha and this is beta. So then we go to the other side and go, well, what's that equal to? Well, it says express it as a sum or difference. Well, that's the right side. That's what we need to do. So it'll be 2 times the sine. It looks like you're doing alpha minus beta over 2, and then cosine of alpha plus beta over 2. If we do a little bit of simplifying in order to make this work, it'll be 2 sine 4x over 2, cosine 10x over 2, which will give you 2 sine 2x, cosine 5x. Okay, so take a note here. This would be the answer to the problem, which can't be simplified, but you'll notice that in here, in doing these problems, I always had brackets set up here and everything. You don't need brackets because these are these are all multiplications. So this is basically 2 times sine 2x times cosine 5x. No distributive property or anything. That literally is the answer to the problem. Okay, one more, alpha and beta again. So remember in both of these, so this is not sine 4x, this is not cosine 5x. That is illegal, as we said in the other, the end of the other problem. So just be aware of that. Students will just do that because, hey, it looks good. Don't do that. So what are we doing? We're looking for the cosine of a sum, which is this guy here. So we're going to use that in order to hash this problem out. I'll leave it at the top here. So again, we're going to get 2 cosine of alpha plus beta over 2, and then cosine of alpha minus beta over 2. Okay, again, simplify. 2 cosine 5x over 2, cosine of 1x over 2. And notice there's nothing else we can do. In the last problem, we were able to simplify here. This one we can't, and we leave it this way. Please, no decimals. I don't want to see a 0.5x or a 2.5x. Remember, whenever we're doing any type of trig, we keep it in the expression to fractional values. Okay, and just to be clear, in each one of these problems, we took a sum or difference between two trig functions entirely and made them into a some type of product, hence a sum to product formula. I know one's a difference, but that's what they're used. They're called sum to product formulas anyway. Okay, so again, just like last time, how can we use this in a setting where now instead of variable angles like we have here and here, we have now actual radian angles. So a lot of times in this section we talk more about like proving something is true or not true. So for example, a student might look at the sine of pi over 3 plus sine of 2 pi over 3 and say, oh, that's got to be equal to the sine of 3 pi over 3, right? Well, as you know, you cannot take these expressions and add these angles. That is illegal. So this is absolutely not going to be true. But why not prove that using our formulas as sort of ammo to do so? Why not, right? So it says here, prove that the sine of pi over 3 plus the sine of 2 pi over 3 is equal to the sine of 3 pi over 3. Prove that is not true using the sum of the product formula on the left side and comparing it to the right side. So why are they saying compare it to the right side? Well, for this one, we know the sine of 3 pi over 3 is equal to the sine of pi. And if we go to our usual setup, pi is over here at negative 1, 0. And we know that when we actually find the sine of pi, we want the y coordinate, which is going to be 0. So we're basically, in this scenario, proving that the left side of this cannot be 0. That's pretty much the idea to the problem. So just realize that's where we're going with it. So if you go over to the sine of pi over 3 plus the sine of 2 pi over 3, we can actually change that using our formulas. So if we go up to our formulas up here, we have the first one is sine plus sine, so now we're going to turn it into this on the left side. So if we do so, we're going to get 2 sine of, so remember this is alpha and this is beta, 2 sine of pi over 3 plus 2 pi over 3 all over 2, cosine of pi over 3 minus 2 pi over 3 all over 2. If we do a little bit of math here, this is a little bit more complicated. So note the sum of these two is 3 pi over 3, or just pi. So we're going to get 2 sine of pi over this 2 right here. On this side, we're going to get negative pi over 3. But if we do negative pi over 3 divided by 2, that's negative pi over 6. So we're going to get negative pi over 6. Okay, so back up to here. So remember, pi over 2 is up here at 0, 1. The y-coordinate is clearly 1. So this is 1. Negative pi over 6 is going to rotate into our fourth quadrant, which happens to be where cosine is positive. Remember, pi over 6 families have root 3 over 2, 1/2 as the coordinate, or variations of that. We want the x-coordinate, which is root 3 over 2, which has to be positive because we're in the fourth quadrant. So if we do the math, we get 2 root 3 over 2, which is root 3. Okay, so we just proved, because the right side is 0 and the left side is root 3, that this absolutely cannot be true. Okay, so last problem in the section. Let's say, once again, we were asked about a verifying identity problem. So let's verify the identities. So if you look over, clearly the left side is absolutely nuts. But if you look at the left side on the numerator and the denominator, we have the sum or difference of two individual cosine sine quantities, which plays right into the formulas in this section. So went too far. Oops. So these formulas here plays right into them. So what we're going to do is we're going to change the left-hand side to make this work. So note, the difference of the cosines is the example where it's a -2 in the front. So it's going to be -2. We're going to get the sine of alpha, which is 3x, plus beta, which is x, over 2. And the sine of alpha minus beta over 2. And that's our numerator. Okay, so you can check that when you look at the formulas and do it yourself. In the denominator, we're going to get 2. Sine of, again, alpha plus beta over 2. Cosine of 3x minus x over 2. So, very interesting development. So every entity in this entire, it's all multiplication. Obviously, what's inside, parentheses is not, but that doesn't matter. Those are just basically the angles of the trig function. So we have a lot of things to sort of cross out. So like this and this end up being out. So we end up with just a negative in front of this sucker. So for the whole thing. Then we're going to get the sine of 4x over 2, which is 2x. We're going to get the sine of 2x over 2, which is just x. The denominator, we're going to get sine 2x and cosine x when we simplify these guys, which is really neat because these guys are now canceling, and we're going to get negative sine over cosine, which of course everybody knows is negative tangent x, which is our right-hand side. So that's a nice little straightforward proof for you.